Hello, welcome to NPTEL online certification course on Introduction to Application of AI to Robotics. Today we are going to discuss about manipulator dynamic equation in the state space form. Okay, so I expect that by the end of this lecture you will have the skill to represent and solve a dynamic manipulator equation in state space form. So, here are the content. The structure of manipulator dynamic equation we will be looking at how it looks like in the state space form and in the configuration space form. Okay. And then we will be formulating manipulator dynamic equation in the Cartesian space, followed by Cartesian configuration space torque equation, and we will be seeing the inclusion of non-rigid body effects such as friction, and at the end I will discuss about the dynamic simulation. Okay, so the structure of a manipulator dynamic equations in the state space form looks like something this. This we have already seen previously, where which is given by tau as mass matrix into the acceleration vector, and then you have centrifugal and Coriolis term, and then you have the gravity terms, okay, a vector for the gravity terms. Alright. So, here basically the tau is the joint torque vector, okay, and this m theta is a n cross n mass matrix of the manipulator. V theta theta dot is n cross 1 vector of centrifugal and Coriolis terms, and g theta is a n cross 1 vector of gravity terms. Okay, so you see this means that the mass matrix is a function of theta, and your centrifugal and Coriolis terms, they are going to be function of theta theta dot. Okay, that vector is going to be function of theta theta dot, and gravity vector is function of theta. So, you see each element of m theta and g theta is a complex function that depends on the value of theta, that is the position of all the joints of the manipulator. And here each elements of the v theta theta dot is a complex function of both theta as well as the theta dot. Let us look at the same example which we have seen previously. It is a 2-arm planar manipulator with the point mass at the end. So, for this manipulator, say if I am asked that okay, you find out what are this mass matrix, what are the centrifugal and Coriolis term, and what is the gravity vector. Okay. So, this equation which we have evaluated using the Newton-Euler method, Newton-Euler algorithm in our dynamics lecture. So, this equation I can rewrite in a different form so that to appear it in this form. So, to do that, let me write the torque vector here like this, and then we can see that we have the acceleration vector here. Okay. So, I can identify this acceleration vector, okay, having the theta 1 double dot and theta 2 double dot term, and then you have this Coriolis and centrifugal terms, and you have the gravity vector over here. So, I am writing this, let us take the first equation. So, I can segregate the coefficients of the theta 1 double dot. So, I have m2 L2 square here. So, I write m2 L2 square here. Then what else is there in the theta double dot? So, this is 2 m2 L1 L2 C2. So, I write it over here. And then another theta 1 double dot term is m1 plus m2 L1 square. So, this whole term, so I write it over here. All are the forms of tau 1, and then the terms associated with theta 2 double dot. So, it is m2 L2 square. So, I write it here. Then here this is m2 L1 L2 C2. And yeah, we are now not left with any theta 2 double dot term. So, this way tau 1 for this part completes. Then I can write the other terms here. If other terms we look at, so I have this square term, okay, that is the joint velocity square term. So, I write it over here. okay, and this term also where we have the product of joint velocities. So, I write it over here, and these two terms have the g components, okay, g term is there, that is gravity. So, I write all those here, okay. Next I move on to tau 2, okay. So, again I identify the terms associated with theta 1 double dot. So, m2 L1 L2 C2 is here. So, I write m2 L1 L2 C2. Then other term with theta 1 double dot. So, this is m2 L2 is square, right. So, I write that m2 L2 is square over here, okay. Then I identify term associated with theta 2 double dot. So, those terms are this m2 L2 is square. So, this m2 L2 is square I write, and that is all. So, this is done. Then I go for the joint velocity square term. So, this one is there. So, I write it over here, okay, and then the g term over here. So, it is only one term. So, that I am writing here. So, this way I can write this equation, okay. Now, let us analyze these terms in details, okay. So, first is the mass matrix. So, we can see these terms associated with the mass matrix, that they are functions of theta, that is theta vector, okay. So, they are functions of theta. So, you have the terms related with theta over here, okay. And this mass matrix, if you look at this matrix, okay, so this term is same as this term, alright. So, if you take transpose of that, you are going to get the same equation, right. So, that is why we call it that the mass matrix is symmetric, okay, and it is a positive definite, and so therefore, it is always invertible. Next, let us look at second term here v theta theta dot. So, as I was telling, we have the term where we have the two joint velocities multiplication. These terms are what we call as the Coriolis terms, okay, and it is caused by the Coriolis force, and these joint velocity square terms, we have the square of the joint velocities, and that we call as caused by the centrifugal force, okay. So, this is explanation about v theta theta dot, and the gravity term g theta contains all terms in which you have the gravity constant g appears, okay. So, you have g here, and you see that you have the theta coming over here, that is cos theta 1 here, cos theta 1 plus theta 2, which means that this term depends on theta and not on its derivative. Okay, so previous form of equation which we have seen over here, here you see this mass matrix is function of theta, gravity terms are also function of theta, but this centrifugal and Coriolis force term, they are function of both theta and theta derivative, okay. So, if I split up this term such that they are the associated matrix are function of theta only, then that what we call as the configuration space equation, okay. So, in configuration space equation, this v theta theta dot I am writing basically as two separate terms here, that is b theta into theta dot and c theta theta dot square, okay, and these are the same term. So, here basically what I am doing is I am making this term only function of theta as well as this term only function of theta, okay. So, here this b theta is a matrix of dimension n cross n minus 1 by 2 of Coriolis coefficients, because you have the two velocities joint velocities product over here, and that is theta dot, this is of n into n minus 1 by 2 cross 1 vector of joint velocity products, and this can be given as here say theta 1 dot, theta 2 dot, theta 2 dot, theta 3 dot, and so on, okay. Similarly, the c theta, it is a n cross n matrix for centrifugal coefficients, and this theta dot square is a n cross 1 vector given by this way, okay. So, you have the theta 1 dot square, theta 2 dot square, and so on, okay. So, now again let us take up the same problem which we have seen previously, and we have written the dynamic equation of this planar 2 degree of freedom manipulator problem with mass at the tip, Okay, so this is the expression. Now here let us split this V theta dot term, okay, into the configuration space form. That is, I want the associated matrix to be function of theta only. Okay. So, this is my V term over here. Okay. So, this V term I am splitting as a B theta and C theta term as discussed previously. So, here this theta dot is nothing in this case, it is theta 1 dot and theta 2 dot because we have only two joint angles, right. So, that is there, and theta dot square means it is a vector, theta 1 dot square and theta 2 dot square. Okay. So, from this expression I can now segregate B theta. What is B theta? B theta is nothing but the product of theta dot. So, I have theta dot here, theta 1 dot, theta 2 dot here. So, this is the term which is going to be there. Okay. So, in the first row this term is going to be there, and in the second row we do not have any term like that. So, we put it up at 0. Okay. Then for the C theta, again this C theta is going to be multiplied with your theta dot square vector. Okay. So, naturally it is going to be a 2 cross 2 matrix, because this 2 cross 2 is going to be multiplied with 2 cross 1, right. So, let us look at what are the products of the theta dot square term here. So, we do not have any theta 1 dot square. So, I put it at 0. Theta 2 dot square term is this one. So, I put it over here, and in the second row I do not have theta 2 dot square term. So, I put it 0 here, but I have theta 1 dot square term, this one. So, I put it like this. Okay. So, this way you see I have written this manipulator dynamic equation, okay, in this particular form, where my B and 3 C matrices, they are function of thetas only. Okay. So, this is what we call as the configuration space equation, because the equation is written in terms of the thetas. Okay. That is the matrices representing the dynamics here, they are function of thetas only. Okay. Next, let us look at the manipulator dynamic equation in the Cartesian space. Okay. So, this is my manipulator dynamic equation in the joint space, okay, where we have the joint position and velocities, okay, and this is the joint accelerations, alright, and these terms are the mass matrix, centrifugal and Coriolis terms, and the gravity term here. So, in case of Cartesian space equation, I can write as F, and this mass matrix I am putting a subscript here, say chi x, and this chi double dot. Okay. And this one I am putting the Vx, and here I am putting Gx, just to represent that they are vector in the Cartesian space. Okay. So, here F is a force torque vector acting on the end effector. Chi is a Cartesian vector representing position and orientation of the end effector. Okay. And mx theta is a Cartesian mass matrix, Vx theta dot is a vector of velocity terms in the Cartesian space, and Gx theta is a vector of gravity terms in the Cartesian space. Okay. So, this way I can represent. Now, to connect both of these, okay, that is the joint space and the Cartesian space equation, let us evaluate fictitious forces acting on the end effector. Okay. F could be applied by the actuators at the joint using this relationship. This relationship we have already seen when we have seen the static forces acting on a manipulator. Okay. So, that time we have studied that one. Here this J theta is the Jacobian, written in same frame as F, and chi double dot, usually the tool frame. Okay. So, this is my equation in the joint space. So, what I do, I multiply with Jacobian transpose inverse here. Okay. In order to get the F value, I have to multiply this tau with the Jacobian transpose inverse. So, I do that. So, this is what I get over here. I put it in this term, this term, this term. Okay. Now, this I can replace as F from here, and the other terms are as it is. Next, we can see the relationship between joint space and Cartesian acceleration. This Jacobian is defined as, we know that this Cartesian velocity vector is equal to Jacobian into the joint space vector. So, if I take the double derivative over here, okay, for this one, so this will be Jacobian derivative into this theta dot plus Jacobian into theta double dot, okay. I am doing differentiation by part. So, from here I can evaluate this j theta double dot, okay, which will be chi double dot minus this one, and so from here I can get this theta double dot, okay. I multiply with j inverse both the sides. So, this is what my equation is. Now, I can substitute for this theta double dot, okay, in this equation which we have derived previously here, okay. So, let us do that. So, in this equation I am putting a theta double dot value, okay. So, this is the first term after putting theta double dot, that is I have j transpose inverse here m theta as it is, and this theta double dot I am putting now this value, okay. So, I have this j inverse chi double dot, and this is again, this is other term is j inverse j theta dot. So, I have j inverse j theta dot this term, okay. Other terms are as it is. Now, I can write this in this form, okay. So, for this blue color expression I am writing as mx theta, this red color I am writing at vx theta theta dot, and this the black one I am writing at gx theta, okay. So, this is nothing but this is what is explained here, mx theta vx theta theta dot, and here it is the gx theta, okay. So, this is how it is. So, here the Jacobian appearing in equation is written in the same frame as f and chi, okay. The choice of this frame is arbitrarily. Now, when the manipulator approaches a singularity, certain quantities in the Cartesian dynamics become infinite. So, these things we have to take into picture when we are designing a manipulator. Okay. So, now let us take again the same example. I am taking the same example so that you have a feel how the expressions are different form. So, for this same problem, the 2 degree of freedom planar manipulator problem with the point mass at the end, here say m2 and m1, we derive the Cartesian space form of the dynamics of this 2-link planar manipulator with point masses at the distal end. So, for this the Jacobian we have already seen, this one Jacobian represented in terms of the frame 3, this one we have seen, this was our frame number 3, okay, with this as x3 y3. So, this is that Jacobian, and I can write the inverse of this one, okay. So, to get the inverse of a 2 cross 2 matrix, here we just interchange these two terms over here, okay, and we put a minus sign on this term, alright. So, this way I get, and then I can get the time derivative of the Jacobian. So, if I want to have the time derivative of this, so it will be L1 cos theta 2 dot, okay, 0 for 0 here, and this one L1 sin theta 2 dot here, and 0 over here, okay. So, we have taken the derivative of the Jacobian, and so these are the terms in the Cartesian space, the Cartesian mass matrix, Cartesian Coriolis and centrifugal forces terms, and the Cartesian gravity vector, okay. So, I can substitute these, okay. So, we have evaluated Jacobian transpose inverse, okay, Jacobian inverse, and these m theta, v theta dot and g theta, these I can get from this equation, right. So, I am not doing all these manipulations, substitution and then evaluation in order to save time, okay, but I advise you to do it yourself. You can do it either in the MATLAB or say any of the Python environment, say, okay, but I will suggest you to do with hand so that you get a feel of the terms. So, this is how mx theta looks like, this is how the vx theta term will look like, and this is how the Gx theta term will look like. Okay, next let us look at the Cartesian configuration space torque equation. Okay, so to do that, here what we have done is basically we have the tau as Jacobian transpose into the force, right. So this force in the Cartesian space, okay, that is the force acting on the end effector, that I am replacing with this term. Okay, so I can replace that and then I multiply with the Jacobian transpose here, so to this term, and say my multiplication of Jacobian transpose with this centrifugal and Coriolis term over here in the Cartesian space, that is split up into the configuration space term like that. Okay, and then again this multiplication is written like this. Okay, so here Bx theta is a matrix of dimension n cross n into n minus 1 by 2 of the Coriolis coefficients, and your theta dot is n into n minus 1 by 2 cross 1 vector of joint velocity products given by this one, theta 1 dot, theta 2 dot, theta 2 dot, theta 3 dot, and the last term is theta n minus 1 derivative and theta n derivative like that. Okay, and Cx theta is a n cross n matrix of centrifugal coefficients theta dot square, and theta dot square is an n cross 1 vector given like this. Okay, in this case we can see that Gx is the same as in the joint space equation, but in general your Bx theta is not equal to your B theta and Cx theta is not equal to C theta. Okay, this value corresponds to the Cartesian space and these values are that from the joint space. Okay, next let us look at the inclusion of non-rigid body effects. So, the dynamic equation of the manipulator which we have seen till now, we have not taken friction into the consideration at any stage. Okay, either the way I have dealt with the Newton-Euler or with the Lagrangian, okay, we have not considered the non-rigid body effects, alright. So, you see friction is responsible for almost 25% of the torque required to move the manipulator in a typical situation. So, almost it is 1/4 of your torque is needed to overcome the friction, alright. So, there are various ways of incorporating this, okay, that is the modeling of this friction. Okay, this friction can be modeled as a say viscous friction. We can have the simple friction model where we say friction torque is the coefficient of friction into the joint velocity. Okay, so that is there, or another possible simple model could be the Coulomb friction. Okay, which is actually a constant except for a sign dependence on the joint velocity. So, the sign dependence on joint velocity is taken by care by this function. Okay, so the value of function is going to be how your velocity is. Okay, and this is the your a constant value which we call as the Coulomb friction constant. So, a reasonable model is the one which includes both, right. So, which includes both, that is the dry friction as well as the your viscous friction. So, that is very much close to the reality. Okay. So, we can see that the complex friction model would be of this form, that is it is going to be a function of both theta and theta dot. Okay. So, I can write the general expression for the dynamics, that is I can add this term extra here, that is the friction torque basically, right, in the other terms of the dynamic expressions which we have derived previously. Okay. Also here we have neglected some other effects in the model. Okay. For example, we have assumed the rigid body link, okay, but actually your body is not going to be rigid. Okay. So, when we are assuming the rigid body link, we are not including the bending effect basically, okay, and that may give rise to resonance. So, again that assumption is over here and this equation is with the rigid body assumption. The last part of today's presentation is the dynamic simulation. Okay, so this dynamic equation has got two uses as discussed previously. Okay, that is the first use is that if I know all these terms, okay, I can find out how much joint torque I need. for a certain velocity and acceleration of the joints, and that gives me an estimate of my motor torque requirement, or what we say that the sizing of the motor. Okay. The other application of this equation is that in simulation. Okay. So, simulation means if suppose I know the joint torque, can I predict what the joint velocity, acceleration and joint position are going to be there? So, that I can do over here by writing this dynamic equation in this form, that is I am taking all these three terms to the left hand side here, and so theta double dot is m inverse theta and this term. Okay. So, I can use the numerical integration technique to integrate this theta double dot in order to get the theta dot and theta values. Of course, we need to know the initial conditions. Okay. So, say at t is equal to 0, theta 0 is theta 0 here, and theta dot at time 0 is say 0. Okay. So, I can carry out Euler integration here. So, theta dot at t plus delta t is theta dot t plus multiplication of acceleration with the time increment. Okay. So, this way I can get this theta dot, and using this theta dot here, okay, theta dot multiplied with delta t, and this one theta double dot multiplied with delta t square into 1 by 2, I can get the value of theta at the time t plus delta t, of course, if I know the value of theta at time t. Okay. So, this way I can simulate my manipulator. So, to summarize, this is the state space form of manipulator dynamic equation in the joint space which we have seen, and this is the state space form of the manipulator dynamic equation in the Cartesian space. So, with this I would like to conclude today's lecture, suggest you to go through some of the practice problems and try to solve both type of problems, that is for the given joint velocities and accelerations, and of course manipulator parameters, find out the torque requirement of the motors, and if you know the torque, then try to find out the joint velocity and positions. Okay. So, these are the references which you can look at for further reading, and thank you.